Hello, ladies and gentlemen. Hope you're all doing well. We're up to question number 4 on the 2000 Euclid paper. It's a two-part question. Let's take a look. As usual, we're looking at a light bulb question for part A. That's pretty standard at this point. So, A says, a die with numbers 1, 2, 3, 4, 6, 8 on its 6 faces is rolled. After this roll, if an odd number appears on the top face, all odd numbers on the die are doubled. So we roll our dice, maybe a 3 pops up, then the die, we erase the 1 and the 3, we draw in a 2, because that's 2 times 1, and a 6, because that's 2 times 3. The numbers are doubled. If an even number appears on the top face, all the even numbers are halved. So we roll and the 8 pops up. Suddenly our dice now reads 1, 1, 3, 2, 3, 4. If the given die changes in this way, what is the probability that a 2 will appear on the second roll of the die? Okay. So we have two possibilities. On the first roll, we get even or odd. Are they equally likely? No. This is something that some people can have trouble grasping. There's 2 outcomes, even and odd. You would assume it's 50-50 chance. This is not the case. Because of our possible outcomes, there are 6 of them. They are what's equally likely. The odd ones, there's 2 of them, but the even ones, there's 4 of them. So it's twice as likely we're going to get an even side face up than an odd side. Okay? So on our first roll, we can either have an even outcome or an odd outcome. So the probability of getting an even outcome is, well, actually the probability of any outcome is the number of the desired outcomes, so the number of even possible outcomes, the number of even faces, over the number of total outcomes. So even, well, what even sides of the dice do we have? 2, 4, 6, and 8 over 6 sides on the die. That's 4/6 or 2/3. The odd should be the remaining 1/3, but let's just double check. We can have a 1 or a 3, and we do count multiples, except there are no multiples right now. So 1 or 3, that's 2 possible outcomes out of 6 total outcomes. So that is 1/3. So with 2/3 of the time, we're going to get an even number on our first roll, and 1/3 of the time, we're going to get an odd number. Okay? So if we get an even number, excuse me. If we get an even number, our die changes, and if we get an odd number, our die changes, and that affects the outcomes for the second roll. So let's suppose for a second we got an even number. Then our die changes to have what faces? If it's an even number, all the even numbers are halved. So 2 becomes 1, 4 becomes 2, 6 becomes 3, and 8 becomes 4. So we still have the 1 and the 3 from before, but now we have a 1, a 2, a 3, and a 4. Okay? And on the second roll, we don't care whether or not it's even or odd. We want to have an outcome of 2. Well, there's 1 out of 6. One out of 6 ways to get a 2 on the second roll. If we know that the first roll is even. Okay, so this happened with probability of 2/3, and then getting a 2 happens with probability 1/6. Now, what are the odds that we're going to get a 2 if we know that our first roll was odd? We have an odd number, then our die reads, all the odd numbers are doubled. So we get a 2, a 2, a 6, a 4, a 6, and an 8. Now we have 2 ways out of 6 to get the number 2 to roll, to roll face out. There are 2 of the outcome we desire, the 2 2s, and 6 possible outcomes. So even, and we get a 2 with probability 1/6, and the evens happen with probability 2/3, and odd happens with probability 1/3. This is a probability tree that I'm drawing. And in this case, we have 2 2s, so the probability of a 2 is 1/3. Now, to figure out the total probability of getting a 2, we need to add up the individual probabilities in each different branch. Okay? How do we figure out these probabilities? For single lines, so for a single connected segment here from the start, to figure out the probability of getting this 2 on the second roll, you have to multiply its individual probability with the probability of even being in this branch, which is 2/3. So, you need 2/3 times 1/6. That's the overall probability of getting a 2 and being in the even branch, plus the probability that you're in the odd branch, and then the probability of getting a 2 in that odd branch. Okay? And this turns out to be 1/9 plus 1/9, which is 2/9, and that's going to be our final answer. So we used a quick probability tree to adjust for the fact that although the face rolls are equally likely, sometimes 2s and 3s are different probabilities because of how many 2s and 3s there are. So we make a probability tree to account for the fact that maybe we get into that odd branch 1/3 of the time and the even branch 2/3 of the time, and we have to adjust our probabilities and the faces of the die accordingly. And we get a result of 2/9. Okay? So B part looks like it's quite long in terms of its wording, and we have a little chart that I assume is related to question number 4. And it's a written question. The table below, okay, gives the final standings for 7 of the teams in the English Cricket League in 1998. Okay. I wonder if a cricket fan made this question. At the end of the year, each team had played 17 matches and had obtained the total number of points shown in the last column. Okay. Each win, W, each draw, D, each bonus bowling point, A, I don't know anything about cricket, but I do believe they bowl the ball, and each bonus batting point, B, receive lowercase w, d, a, and b points respectively, where w, d, a, and b are positive integers. So maybe each win is worth 3 points, and each bonus bowling point is worth 2 points, something like that. No points are given for a loss. So, despite the fact that this column is included, I think we can probably ignore it. Determine the values of W, D, A, and B if total points awarded are given by the formula W times the number of wins, D times the number of draws, A times the number of bowling points, and B times the number of batting points. Okay. So basically, we ignore this middle column, and then we have to figure out how do we get 201 points with 6 wins, 4 draws, 30 bowling points, and 63 batting points in a way that's consistent with the rest of the table as well. Okay. So this is actually, in disguise, a great big system of linear equations. Okay, so we're going to take some time. We're going to write it out. If you were doing this question, you might not write the whole thing out. You might start trying to analyze the table like we're going to in a moment, but you might just jump straight to that. So we're going to write out a bit of the table. I'm not going to write the losses columns because it says we don't account for losses at all. Losses are no points, so I don't care how many times you lost. That's not going to contribute to your overall point score. We just care about the wins, draws, bowling points, and batting points. Okay, so we're going to leave losses out of the table. All right. So we had 6 wins in the first one. We multiply that by W. So what we're doing is we're taking our table and we're turning it into a system of equations. So we have 6 wins. We're ignoring the losses. I think it was 4 draws, 30 bowling points, and 63 batting points. And together that gives us 201. Let's just double check. 6, 4, 30, 63. Okay. The next line, again, we ignore losses. So 6 wins plus 3 draws and 35 bowling points and 60 batting points gives us 200. So 6 wins, this time 3 draws, and I think it was 35. And I think we have 6 wins, 4 draws, 30, and I cannot remember what the last number of the next row was. 54, and that gives us a total of 192 points. And as I'm writing out this system of equations, I'm slowly trying to figure out, well, what am I going to do to actually solve for these W, Ds, As, and Bs? What you want to do with any system of equations is you want to start comparing them, adding, subtracting, manipulating them together to start isolating for single variables. Okay? And already in this table, I can already see the first line is 6, 4, 30, 63. And the second line is 6, 4, 30, 54. So if I took the first equation and the third equation, subtracted one from the other, I might be able to very easily isolate B, the weighting of the batting points. All right. Then we have 6, 4, 28, 55, and that gives us 191. (191). 6 wins, 4 draws. Okay. And 5, 4, 4, 7, 7, 7. 5, 4, 4, 7, 7, 7. 18, 32, 36, 59, 59, 55. Those are our batting points. That was 178, 176, 176, and I believe that was 18, 32, and 36, and we're just going to double check that. Because you can write equations all we want, but if they don't reflect this actual table and this actual way of calculating points, then there's really no point to what we're doing. We're making up our own question. Okay, 59, 59, 55. I think we're all set. And we could include the team names in our description, and that's okay. But we're actually just going to number our equations. Alright. So, given this set of 7 linear equations and 4 unknowns, we should be able to solve for W, D, A, and B. Okay, 7 equations, 4 unknowns. We have more equations than unknowns. In theory, we should be able to solve this. Okay, and there's a bunch of different avenues for attack. There really are. One thing that we could say, as I've already mentioned, we could take equation 1, subtract it off equation 3, and we'd just be left with 9b equals 9, and that would immediately give us b. Other things you can do, and there's probably lots of other ones. You might have looked at this system of equations and picked out different equations that you liked and come to the same results in a different way. That's okay. With 7 equations, there's lots of different ways to handle this question. Another really sort of easy way to do it is take that first equation, move the 63b onto the one side, the 201 onto the other side, and divide by 63. Suddenly you've got an equation for b, and you could substitute that in to every other equation. Now, if you do that, it's going to get messy. There's going to be a lot of fractions. So what we're going to try and do is do some Gaussian elimination. We're going to look for 2 equations that have a lot of the same values in common, and use those to try and isolate for their different values and see if we can come up with much simpler equations that we can use, like 1 and 3. So what we're going to do is we're going to take equation 1, and we're going to subtract equation 3. So that's 6w plus 4d plus 30a plus 63b. That's 201. And 6w plus 4d plus 30a. And when we subtract these two, we get a brand new equation that is just 9b equals 9. And it's not hard to see from here that b is going to have to be 9. We just divide both sides by 9, and we get b is equal to 1. So b equal 1. Okay, that's great. So now we know one of those, and what we could do is we could actually rewrite all our equations, substitute in that b, and you'll get 63, and you could cancel the 63 out with part of the 201, and you'll get 7 equations in 3 unknowns. That's okay. That's a perfectly valid way to do things, but it's going to take some extra time. So let's see if we can just keep our equations the way they are and use our information of b equals 1 in other ways. Now, another thing that I'm picking out is I notice these last 2 equations. They start off 4w, 7d, and there's 32 and 36. That's a difference of 4. 59 and 55, that's a difference of 4. And they come up to the same outcome. So at the very least, we're going to be able to get a relationship between a and b. I can already see that a is going to be equal to b, and since we know what b is, we're going to be able to figure out what a is. So that's 4 wins plus 7 draws plus 32a plus 36a plus 59b plus 55b, and they're both equal to 176. So 4w minus 4w, well, that's 0w. 7d minus 7d, that's 0d. 32a minus 36a, that's negative 4a. Here we have 4b is equal to 0. And if we just bring the 4a over to the other side, we get 4b equals 4a. Or really, b equals a. And therefore, a is equal to 1. Okay. So just with 2 Gaussian eliminations, which is what this style of manipulating systems of equations is called, we are able to figure out a and b. All that's left is to figure out w and d. So we need to start picking other equations. Now, so far, we've had w and d always have the same. We've had the same number of wins and losses that in every single equation we've compared with Gaussian elimination. So maybe we want to isolate for w. Okay, here I notice equation 5 and equation 6. They differ in their w's, but they have the same d's. Okay, so that means if I take 5 and I subtract off 6, I'm going to get a single w, because 5 minus 4 is 1, but I'm going to get no d's. Okay? And I know what A and B are, so I can plug in A is 1, B is 1, and the rest of the equation becomes very simple, and I'll get something just in terms of W. That's 5W plus 7D, 4W plus 7D. I think it was an 18, but let's actually just go back and check. 1832. So 18, and oh, the 59Bs are going to cancel out as well. $178, $176. So when I subtract these, we get a single W, we get 0 Ds, and we get 18 minus 32, so that's going to be negative 14A, 0 Bs, and that's all equal to 2. So we can rearrange this and say W is equal to 2 plus 14A. Okay? A is equal to 1. So we'll substitute that in. 2 plus 14 times 1. And we get W is equal to 16. We're almost there. We just have one more to go, and that's D. And really what we can do is pick any equation. So let's say equation 1. That's, 7W. Actually, let's just pick equation 7, because it's already written out for us. 4W plus 7D plus 36A plus 55B equals 176. So we sub in to solve for D. So we have 4 times 16. That is, that's going to be 64. Plus 7D plus 36 times 1 plus 55 times 1 equals 176. So we get 64 plus 7D plus 36 plus 55 equals 176, or 7D is equal to 176 minus 64, and that's going to be 112 minus 36. So 112 minus 36, that's going to be 106 minus 30, so that's going to be 76. Minus 55, we're going to get 21. And D is going to be 21 divided by 7, so D is 3. So we just group all our information together in the end, and we have our final answer. Now, if we doubted that, and it's certainly possible that we doubted that, maybe we think, oh, 7 equations, 4 unknowns, we did a lot of manipulation there, maybe we made some mistakes. It's okay to take those numbers, the W, the D, the A, the B, and hopefully with 7 equations and 4 unknowns, there's at least one equation you didn't even touch at all. So for example, we never dealt with equation 2 or equation 4. What I would do to check is I would take that W, D, A, and B, what I think is the answer, and I would plug them in to equation 2 or equation 4. If I had time, I'd plug them into all the equations and make sure that they really do work. Check for my sake that I didn't make some silly arithmetic mistake, that I didn't plug in a number wrong on the calculator or hit a minus when I should have hit a plus. Little things we can do at the end to check. Okay? Should we check all of them? It all depends on where you are at with your abilities and how well you think you might do on this Euclid. If you are shooting for question 7, 8, 9, 10, the really hard ones, if you think you have a shot to do well on them, would I spend time, or should you spend time, checking all 7 equations to make sure that your W, D, A, and B all work? Not so much. You want to leave as much time as possible for the really difficult questions that require time, thought, smaller cases need to be worked out, things like that. This question, a simple arithmetic, you lose a mark. But that's nothing compared to not even having the time to try and write up question 9 or 10. Okay? But if you are a first-time writer, or if you're a younger writer, and you think, well, question 4, we're almost halfway through the contest, and I got a lot of time to kill, and I looked at question 7, there's no way I understand it, then yeah, go through and make sure that you have question 4 correct, because if it's one of the few questions you think you can answer, you want to make sure you get as many marks as possible. So that's question number 4. We're almost halfway done, as I say. We'll be on to question number 5 in the very next video. Hopefully you guys have enjoyed it, and until the next video, take it easy.